Hello everyone, we are from Group 22 and our team members are Shravani Manne, Sharing Lama and myself Lakshmi Priyanka Vemra. Today we are going to discuss about the topic paper 2, Mastering the Game of Go Without Human Knowledge. Coming to the abstract, it's an algorithm which requires superhuman ability in tough fields from the scratch is a long-standing objective of the artificial intelligence. AlphaGo just made history by being the first computer program to defeat a world champion at the game of Go. And AlphaGo became its own teacher with a neural network to forecast AlphaGo's own move selections as well as the outcome of its game. In these deep neural networks were used to analyze positions and select moves in this AlphaGo's tree search. And next, supervised learning from human expert moves and reinforcement learning from self-play were used to train these neural networks. Coming to the introduction of the game, in this paper, we are going to discuss how the game of Go has started its evolution and what are the later versions of the game of Go. Artificial intelligence has made greater progress primarily to supervised learning systems, which are training to replicate the decisions of human experts. And the algorithms used here have outperformed people in computer games such as Atari 6, 7, and 3D virtual environments 8 to 10. Here, the most challenging domains is in terms of human cognition, such as the game of Go, which is frequently viewed as a major problem for AI, which demands a precise and intelligent look ahead across various vast search regions. And many general techniques have to attain human level performance in these domains. On the other hand, expert data sets, which are frequently expansive, unreliable, or just unavailable, have been used here. Reinforcement learning systems, on the other hand, are taught by their own experiences, allowing them to theoretically outperform humans in domains where human expertise is insufficient. Coming to the next slide, it tells this slide deals about the how AlphaGo Zero has evaluated. First thing, it was the first Go program to achieve superhuman levels of performance. After AlphaGo was determined, AlphaGo Fan was created, which defeated European champion FanHu game. And using enforcement learning, the network was pitched against itself. And all these games combinedly uses the Monte Carlo tree search, which is an famous algorithm tree search, which produce a look ahead search with the policy network results to those of high quality. After that, AlphaGo Zero has been created, which is entirely different from the AlphaGo Fan and AlphaGo Lee 12 in several ways. Our program is our topic is only about the AlphaGo Zero in this paper. And this AlphaGo Fan employed two deep neural networks. One is a policy network and one is a policy network, which is used to generate move probabilities. And there is a network one, which uses supervised learning value network that used to generate position evolutions. Coming to the next slide, how reinforcement learning is used in AlphaGo Zero. This corresponding diagram illustrates about the self-play and the neural network training and how deep neural networks are applied in this AlphaGo Zero game. The neural network in AlphaGo Zero is trained from self-play games using a revolutionary reinforcement learning approach. In our suggest method, we use a deep neural network F theta with parameters, and both policy network and the value network are merged into a single architecture in this neural network. And a strong policy evaluation operator might be self-play with search, which selects each move using an upgraded MCTS based policy and then utilizes the game winner. Coming to the next slide. This slide mainly discusses about the Monte Carlo tree search and the flow of this research. Actually, in this, all the neural networks commonly follow the same flow of process. It has 4 steps: select, expansion, simulation, and backup. In the select, it starts with the root R and it selects its own successive child nodes until it reaches the leaf node L. In the expansion, it goes on expanding its child nodes. And in the third simulation simulation part, which is also known as playout or rollout, it just complete another one random playout from the node C. And the backup is nothing but it update information in the nodes on the path from C to R using the playout result. Coming to the next slide. Empirical analysis of AlphaGo Zero training. In this, to train our program AlphaGo Zero, we used reinforcement learning pipeline. This figure shows the empirical evolution of the AlphaGo Zero training, in which the plot depicts the performance of each MCTS player and in each iteration of reinforcement learning. And the LO ratings are also calculated using 0.4 seconds of thinking time, each move in assessment games between various players. And training began with fully random behavior and lasted around 3 days without human assistance. Accuracy of human professional movements prediction. This graph also depicts the accuracy of the neural network. Now, my teammate Shravani will continue with the topic.
Hello everyone, myself I'm Shravani. So today I'm just going to continue the presentation on paper 1. About the knowledge learned by AlphaGo Zero. So over the courses of 40 days, AlphaGo Zero learned using a 40 block residual network, and each player's performance in each iteration of the reinforcement learning system is depicted in the graph. And AlphaGo Zero won the end game by capturing races, shape, influence, and territory. So all of these which were uncovered using basic principles. AlphaGo Zero, however, we did not master until like AlphaGo has completed online. And this picture represents the AlphaGo Zero, which are 40 blocks over 40 days versus AlphaGo Master Tournament games using 2H time controls. So here 100 moves of the first 20 games are shown. And coming to the next slide, final performance of AlphaGo Zero. So here in each program, 5 seconds are given per move, and AlphaGo Master and AlphaGo Zero shared a Google Cloud machine, while AlphaGo Fan and AlphaGo Lee share many machines. So the network which select the move with the highest probability PA without MCTS is also included. So each program is given a 75% chance of winning on the scale of 25. And here it shows the frequency of occurrence over time duration training. And here we could see the corner sequences common in professional play that were discovered by AlphaGo Zero. So here frequency of occurrence over time duration training is shown, and the corner sequence that all AlphaGo 0 favored for at least one iteration and one additional variation. So coming to the conclusion, we after going through the paper one, we found out that without human examples or teachings, and it is possible to train to superhuman levels, and a pure reinforcement learning technique also takes less time to learn and produce better asymptomatic results than training on human expert data. And AlphaGo 0 surpassed various AlphaGo versions that were trained with handcrafted features and human data. We were provided patterns, proverbs, and literatures which have emerged from millions of games over thousands of years. So AlphaGo 0 recovered most of this Go experience as well as invention strategies that provide fresh perspectives to the oldest of games in few days. Over to Lam.
Hi everyone, my name is Chunin Rama and I'm gonna cover the rest of the paper called Mastering the Game of Go with Deep Neural Network and Search Tree. The Monte Carlo Tree Search, or MCTS. All game of perfect information have an optimal value information, V star S, which determines the outcome of the game. From every board position or state S under perfect play by all players, these games may be solved by recursively computing the optimal value function in a search tree containing appropriately b to the power d possible sequence of moves, where b is the game's breadth, number of legal moves per position, and d is its depth or game length. For large games like Go and chess, due to the complexity of the game, these games cannot be solved by recursively computing the optimal value function in a search tree containing approximately b to the power b. So Monte Carlo tree search comes into play. Monte Carlo tree search overcomes this problem by using Monte Carlo rollouts. Monte Carlo rollout search to the maximum depth without branching at all. By sampling long sequences of actions for both players from a policy P, averaging over such rollouts can provide an effective Monte Carlo tree search, which uses Monte tree search. And as more simulation are executed, the tree search grows larger and relevant values becomes more accurate. The policy used to select action during search is also improved over time by selecting children with higher values. Furthermore, this policy converges to the optimal value and evaluate the and conversion of the optimal value function. The strongest current Go programs are based on MCTS, which enhanced by these policies are trained to predict human expert movement. These policies are used to narrow the search to beam of high possibility action and to sample action during rollouts. Similarly, AlphaGo. AlphaGo effectively combines the policy and the value network with MCTs. AlphaGo uses deep evolution neural network, which have achieved unprecedented performance in visual dominance. For example, image classification and facial recognition. The neural network for AlphaGo are trained using a pipeline construction of several stages of machine learning. Supervised learning SL policy network, P-alpha, is trained directly from expert human moves. This provides fast, efficient learning updates with immediate feedback and high quality gradient. Similarly, we also train a fast policy PPI that can rapidly sample action during rollouts. Next, we train a reinforcement learning running RL policy network P Lambda that improves the SL policy network by optimizing the outcome of games of self-play. Finally, a value network V theta is trained that predicts the winner of the games played by the RL policy network against itself. Can you change the slide? Supervised learning of policy network. For the first stage of training, we build on previous network on predicting expert moves in the game of Go using supervised learning. The policy network is then trained on randomly a fast rollout policy Pi and supervised learning SL policy network P lambda are trained to predict human expert movement in data set of position. Reinforcement learning of policy network. The second stage of training pipeline aims at improving the policy network by policy guidance reinforcement learning. The RL policy network P lambda is identical in structure to SL policy network and its weight P lambda are initialized to the same value of P equals to lambda. A reinforcement learning RL policy network P lambda is initialized to SL policy network and is then improved by policy and graded learning to maximize the outcome, that is winning more games against previous version of policy network. With the well-trained network, the 13-layer policy network, which we all call the SL network policy, offers 30 million positions from KGS Go server. The network predicted expert moves on held out test set with accuracy of 57% using all input features and 55.7% using only raw board position and move history as input. Compared to the state of the art from other research groups of the 44.4% of data of submission, a small improvement in accuracy led to large improvement in playing strength, larger network achieve better accuracy, but are slower to evaluate during such. Reinforcement learning and value network. Can you go up, please? The next slide, the upper one, yes. Reinforcement learning of value network. The final stage of training pipeline focuses on position evaluation, estimating a value network d to the power p s that predicts the outcome from position S of a game played by using policy P from both players. Vs, where the formula goes, Vs equals to E to the J S equals to pi S. Searching with policy and value network, AlphaGo combines the policy and value network in an MCT's algorithm that selects action by look-ahead search. Each edge is evaluated in two ways, using the value network V theta and by running rollouts to the end of the game with the fast rollout policy P pi. Then computing the winner with the function R. Evaluating the playing strength of AlphaGo. To evaluate the play AlphaGo, an internal tournament among variant of AlphaGo and several other Go programs, including the strongest commercial program, Crazy Stone and Gene, and the strongest open source program, Patsy and Figo. To have ego, the result of the tournament suggests that the single machine AlphaGo is many than ranks stronger than any previous Go program, winning 494 out of 495 Go games against other Go programs. Thank you.